Hi, everyone. So this is a brief introduction to probability, just to make this sort of concept a little bit easier to sort of grasp and wrap your hands around. So I'm going to share my screen. And so one point I'm going to stress in this is that a lot of probability is really all about how you count things. And so you may have done a histogram in class. That's another form of counting things. And when you do a histogram, you're actually creating a form of probability. And so, for example, if I have a histogram that looks something like this, that's been one, maybe it's connecting to the y-axis at 2, that's been 2, maybe it's connecting to the y-axis at 6, that's been 3, maybe it's at 8, then 6, then 2, and that's what my histogram looks like. Then you can actually find probability off of this. You can find, for example, this has been 1. What's the probability that your outcome falls into the first category, the first bit? And how you do that, it's the probability is always calculated as the event you're interested in over the total possibility, the total sample space. And so if we take these values to sort of be gospel, we have 2 plus 6 plus 8 plus 6 plus 2. 2 plus 6 is 8, plus 8 is 16, plus another 8 is 24. So our total sample space is 24. That's all the possible outcomes that fit into this histogram. And then if we want to find the probability of randomly picking the outcome in that first bin, well, there's 2 outcomes in that first bin. So the event we're interested in is 2 over 24 over 1 over 2012. Point being, probability is all about counting. It depends on how you count. So I'm going to, and just for record too, this too is a form of counting. There are 2 counted values in that first bit. That's sort of what I mean by it's all about counting. So for the purposes of this video, I'm just going to go through several ways of counting. And then, we'll go from there in terms of, any questions you guys may have. But just to show you all the different ways of counting and the logic behind them, I think it's important to sort of go through some examples. So the first example is counting when things can be repeated. And so I'm going to use an example here, just a lot. Next, I'm gonna draw just the letters a lot. And this lot has 3 sections where you can put numbers in. And each section where you can put numbers in has 3 possibilities of numbers that you can put into that section. So a question is, how do you count this? This is repeated, meaning that I'm allowing for the fact that you're opening the lock. You could have a password of 222, and that can open the lock. And so how do you count this? If you were in a problem where like you came back from a trip or you're preparing for a trip and you have this old travel lock and you don't know what the password is, how many how many different things do you need to try to open it to work? It's the same kind of idea here. What kind of password do you need to open the lock if you allow that numbers can be repeated. Or if you allow that events can be repeated, you don't lose an outcome on each event. So the way to figure this out is you can start anywhere on this line. You can start on the second part, the first part, the third part. Let's just say we start randomly on one of them. So when you start in this first node has three possibilities of choices that you have. You can either pick 1, 2, or 3. And then once you pick that, remember things can repeat. You don't lose an ability to select any of these. If you select one, let's just say you start right here on this first part of the lock, and you select 1, on the second part of the lock, you can also select 1. You don't lose a choice. And so what the graph looks like is kind of like this, where you still have choice 1, choice 2, and choice 3 available to you. It's the same for if your first pick, your first lock combination uses the number 2. You don't lose the ability to use 2. You still have a choice after that of 1, 2, or 3. And as you can see, it's going to be the same for this one as well. All right, and then you still have another part of the lock to do. You can guess that it's pretty much going to be the same kind of path possibilities. Your final choices have 3 possibilities as well. It's a little hard to draw this, but I'll do my best. So now we get to the final part of this. If we're going to count these correctly, and if we're going to count these in such a way that we can replicate on bigger and bigger numbers, we need to form some sort of math that can help us count in situations where outcomes can be repeated. And so what we know is that one possible outcome exists along this path. Another possible outcome exists along this path. And another possible outcome exists along this path. What I want you guys to see when I'm doing this is this idea that each of these last stubs will form an outcome of this experiment. And so what we're really counting when we do this is each of the last stubs, because they sort of form the entirety of choices that are possible. And if you count this, you get 27 possible outcomes. So if we were to apply a math to this, you might think, okay, maybe we can do 3 plus 3 plus 3. There's 3 choices for the first part of the lock, plus 3 choices of the second part of the lock, plus 3 choices of the third part of the lock. But remember, we're not saying that we selected one pathway. We're not saying we selected going to 1 already. You just want to know how many different ways can this happen. And so if we try this first 2 will get you 6. But notice when you're on the second level, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So that doesn't work. 6 is not equal to 9. So the only way you can count this is if you change pluses to multiplication. And then you get the appropriate number of total possible outcomes. All right. So this is repeated when outcomes can repeat. Another example of this can be, let's say you have a candy jar and you have strawberry, orange, vanilla, and cherry in the candy jar. And you want to know how many different ways you can pull 4 candies out of this candy jar. If you allow a candy to be popped back in once you pull it, then this is the same thing. It's repeated. You can repeat that. But what if you don't allow that? We're going to go non-repeated now. So what happens when you don't allow that? Well, remember we have a jar of candy. It's strawberry, orange, vanilla, and cherry. You can make up your own flavors for this if you want. And now let's say you just want to know how many different ways you can pull 4 candies from this jar containing 4. And you're not going to put them back, you're going to eat them because they're candy, they're delicious. So how do we count this? Well, on the first selection, you have 4 possible outcomes. You have strawberry, orange, vanilla, and cherry. And you can pick any of them. Notice something here. Once you pick strawberry, you've eaten it. So you can't put that back into the jar. So you have 3 possibilities left. Orange, vanilla, and cherry. Then once you pick vanilla, you can't put it back into the jar again because you've eaten it. You have 2 possibilities left, orange and cherry. And then let's just say you picked orange. The only possibility left is cherry. And this pattern is going to go from each choice. Remember, we're not saying that the experiment has proven that we've already picked strawberry. We're not saying that at all. We're saying you just want to know the total number of different ways you can pull 4 from a jar of 4. And we're saying that once you pull it, you eat it. So you can imagine it's different than 3 times 3 times 3 because you lose an outcome each time you pull a candy from the jar. And it becomes the math to solve this, assuming that you're understanding that these all will have their branches. The math to count how many of these different branches end up at the end there becomes 4 times 3 times 2 times 1. And just starting off, you can see why this is the math and it's not 4 plus 3. If we just go to the second stage here, and we counted what's possible in the second stage, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have to have 12 possible outcomes in the second part of this. if we only pulled 2 out of the 4. That's what this math says, because there's 12 of these blue lines. And so 4 times 3 gives us 12, but not 4 plus 3. You can't use plus to do this. You have to use multiplication. All right. Now let's explore this question. What if you do stop at that second stage, or you do stop at that third stage in a non-repeated experiment? It's different if it's repeated. But if it's a non-repeated experiment, what happens when you stop in the middle like this? I've given you a hint here. But let's build it out. So the next sheet we're going to do is, this is what's called a permutation. And here's how we do it. Let's consider a different example. You have 10 horses. Horse 1 through 10. And they're running a race. If you're buying a lotto ticket, you want to know the probability of you winning that trifecta, triple crown winning, which is supposedly the most that you can win. So you have one lotto ticket, but how do you build that probability? Well, you need to know how many different ways can 3 horses win a race. Because in that lotto ticket, when you're betting on the top 3, you only win if your top 3 win. So you only care about 3 selections. So applying this non-repeated logic, and if I were to build this out further, you could imagine other branches sort of growing out of each of these into their own branch, and you can count them. But applying this logic, the 4 times 3, the 4 possible outcomes at first, then once you've eaten the candy, you lose the choice, and you have 3 possible outcomes next. Once you've eaten the candy, you lose the choice, and you have 2 possible outcomes next, and so forth. Applying that logic, let's apply it to the horse example. You start off with all 10 running the race. Only one horse can win. 1 out of 10 can win. Once that horse wins, it's not going to be running across the track again. It can't. They won. They got to give it booze or something. I don't know. They got to put laurel wreath on it or whatever they do with horses. So any of those 10 horses can win. There's 10 possible outcomes. Now, once that first horse wins, what are the number of horses that are still out there? Well, let's just say, for the sake of argument, horse number 10 wins. So who could win second place? Any of the 9. What happens in this example is that any of the 9 remaining horses can win second place. And then let's say horse number 9 is the one that wins second place. Then any of the 8 remaining horses can win third place. And all you need to do is take it that far. There's a lot of fancy math in textbooks and stuff, but really what a permutation is, it's just saying, okay, I want to count what are three out of 10. how many different ways can I get 3 out of 10? And so the first option, there's 10 choices. In the non-repeating way, once I pick one choice, it's gone forever. So there's 9 choices left. And once I pick a choice, it's gone forever. So there's 8 choices left. It becomes 10 times 9 times 8. Doing that math and solving this probability is 10 times 9 times 8, or 720. And so the probability of a triple crown is 1 over 720, or about 0.1%, which is what appears on the screen when you just sort of expand the screen like that. Now, one other thing that's important in this, if you consider the groupings of horses, 1, 2, 3 can win, 4, 5, 6 can win in the first 3 slots, 8, 7, 6 can win in the first 3 slots. This 720 gives you the total possible outcomes of 3 out of 10. But it's not going to be sensitive to like the difference of if horse 1 wins first, horse 2 wins second, and horse 3 wins first. Or if you reverse that, horse 3 wins first, horse 2 wins second, and horse 1 wins first. I think sensitive is maybe the wrong word to use, but I use that both of these are distinctly different outcomes. If you're playing the lottery, for example, and you were betting on the horses, and you said 1, 2, 3 would win, but 3, 2, 1 wins, you lose that lottery thing. It matters the selection. And more importantly, the selection counts as a distinctly different outcome when you count them in this permutation method. 1, 2, 3 is distinctly different than 3, 2, 1. They are different outcomes. Let's go to our final example. You may have a situation though where they're not supposed to be different outcomes, where 3, 2, 1 means exactly the same thing as 1, 2, 3. Meaning those two outcomes really need to count as one. Let me give you an example where that might occur. Let's say that you have a situation where you are pulling candy out of the bag. I like this example because I like candy. So you have a bag and you're pulling candy out of it. Chocolate, vanilla, strawberry, and blueberry. Let's just say. And you're pulling 3 out of 4 out of this bag. And you want to know how many different ways you can pull 3 out of 4. You equally like all of them. So it doesn't matter to you if you pulled cherry first or vanilla second or blueberry third, or blueberry first, vanilla second, and I think there's some chocolate, but I'm going to change it to cherry third. You just like this bag of candy. So you don't care sort of what your first bite is. And so how do you count this? Well, you can take a guess and sort of say, okay, we did this once before. It was 4 times 3 times 2 times 1. And then we learned about this permutation thing. And we saw how you can sort of take a group out of a larger group by just counting the number of different times of occurrences of that smaller group, like I've done here. But now, let's try that here. Let's say, I don't care if cherry, vanilla, and blueberry are the same or not. We can have them count as one. So let's try permutations first and see if that works. So you have four choices here. And then you have three choices after you picked one. So after you pick chocolate or cherry or whatever it is, there's three choices left to you into each of these possibilities. And then after you pick the next candy out of the bag, there's two left. So one, two, 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 and then there's not one left. Because once you pick this last candy, and let's say you're in each of these nodes, this is a choice of picking, these are choices of picking, and then these are choices of picking. Notice just by looking here, you have three nodes of picking. You pick three times. You pick three times. 1, 2, 3. 1, 2, 3. And I'm just mapping out, remember, I'm mapping out all the possible ways you can pick three times. But you don't have a fourth chance to pick. So if we're doing permutation method, we're doing 4 times 3 times 2 to count up all these little sort of extensions. You have 6 extensions here, 6 here, 6 here, 6 here. So this must equal 24, and it does. But remember, I said you don't care if 3, 2, 1 or 1, 2, 3 exists in this sample. You don't care if you pull cherry first and vanilla second, or vanilla first and cherry second. Your order of selection, the selection you have, that selection, as long as everything's the same candy, doesn't matter what it was picked. Anything that's the same candy is counted as one event. So permutations, we come up with 24 by using that method. But remember, here, force 1, 2, 3 is a different outcome. It counts differently. You don't win the lottery if you're 3, 2, 1, and it comes out 1, 2, 3. In this example, it doesn't count differently. It doesn't matter if you pick cherry and blueberry first and second, or blueberry third and cherry second. As long as it's in the same grab of 3, you're good. So if you said 24 is the answer to this, there are 24 ways we can pull 3 from 4, or choose 3 from 4. You'd be wrong. And the reason why is, remember, we don't care the order of the selection here. So if we don't care, there are 3 things we're pulling from this. We can either pull cherry, vanilla, or blueberry. And we don't care what order those come in. So we know there's 3 possibilities at first. You don't care what order those come in. Doesn't matter if vanilla comes first or not. But once we pick the first one, we lose that option. There's 2 left. Once we pick the second one, we lose that option, and there's 1 left. So we just consider the isolation. There's 3 possibilities here. And we consider how many different ways 3 can occur. The 3 we're pulling can occur. And this could be any 3. I'm just picking CVB out of the hat, but it could be CSB. We just want to know how many different ways 3 can occur. You can use permutations as well. So what ends up happening, we know permutations doesn't account for 1, 2, 3, and 3, 2, 1 being the same thing. It combines them into one outcome. So if you wanted to do that they are the same thing, then it doesn't matter cherry is first or blueberry is first or vice versa. Then what's going to end up happening is that you have to adjust this permutation by another permutation to get the right outcome here. What you get is 4 possible ways. You can choose 3 from a bag of 4, where it doesn't matter the order of the selection, where if blueberry was first and cherry was last, or cherry was first and blueberry was last, that doesn't matter. Finally, in Excel, this 4 is called a combination. We've calculated a combination. And in Excel, the formula to get this 4 is equals combin. Open parentheses and close parentheses. If you do the same thing to permutation in this tab, the formula is equals permute. Open parentheses and close parentheses. And when you do this, let's do it for the horse example. Equals permute. The first argument in both of these is going to be the total number of different things in your sample. So there's 10 horses. And the second number is going to be what you're choosing from that sample, which is 3. Notice how I got the same 720 by doing that. Combination is the same argument. Total number, there are 4 candies in the sample, we're choosing 3. And we get 4. Finally, the confusion in this is a lot of times people will say order matters or order doesn't matter to distinguish the two of them. It's better that you think of it as the order of the selection doesn't matter, i.e. combinations, or the order of the selection does matter, i.e. permutations. And more importantly, take the word matter out of there. And just consider that with combinations, the only difference is what you're adjusting for is the fact that these 3 choices from the candy bin can be in any order, and it doesn't matter what the order is. You can have cherry first and blueberry second, or vice versa. So you're going to have to adjust for that 3 by putting a permutation underneath a permutation. I hope this was helpful. This is just a brief introduction on sort of probability and counting. When you get further into this, you'll get into something called like conditional probability, for example. And something like that is, remember I said these examples, we hadn't actually chosen one yet. We're just looking at the total possible outcomes. Well, for example, conditional probability is what do you do if you've chosen one? Sort of how do you count probability if you've already known that you've chosen that door and it doesn't work, or you pick this first number and it doesn't work. There's other things called independent events you'll learn about, and sort of joint probability, intersections, unions. That's all for a later video, I think. But I'm hoping that this sort of gives you a start as to sort of this complicated subject here. Thanks. Bye.